we draw the conclusion that the kinetic energy differs even though you have the same total mass at the same average distance from the axis. In other words, 50 grams at 9 centimeters and 50 grams at 11 centimeters is 100 grams at what average distance? 10 centimeters. Two 50-gram masses at 10 centimeters is, again, 100 grams at an average distance of, well, 10 centimeters, since the distances are both the same. However, when moved at any angular velocity, the kinetic energy of the 9 centimeter and 11 centimeter is about 1% more than that of the two masses at 10 centimeters. And it just means that it's an instance of the fact that the distance from the center has more effect than the mass on the moment of inertia. Now, that's what you expect, since the moment of inertia of a point mass is mr squared, where r is the distance from the axis of rotation. R squared is not linear. We would not expect the result for these two distances to be exactly the same as for this distance, because averaging these two distances is a linear process. We average the first powers, and that's not appropriate to the situation because of the r squared here. And again, we see clearly in terms of this example that it doesn't quite work out. So that's kind of an important thing to understand about moment of inertia, but it's one of the finer points. At the bottom line, you should understand how we calculated these kinetic energies, and you should be able to corroborate or critique my calculations. Okay, well, there's another way we could have calculated the kinetic energy, and that's 1/2 I omega squared, where I is mr squared. Now, moment of inertia of any mass is mr squared, any point mass, the mass at any point, and we assume that the mass is concentrated at that point, even though that's not quite the case. And we get around that using calculus in a way that you don't need to worry about. So, if we have a 50-gram mass at 10 centimeters, its moment of inertia is 50 grams times the square of 10 centimeters. Right there's the calculation. And it comes out 5,000 grams centimeters squared, or 0.0005 kilogram meters squared, if you wish. Because 5,000 grams, for example, is 5 kilograms. It takes 10,000 centimeters squared to make a meter squared, so this is going to be 1/10,000th, and that's what we end up with. Okay. And then the kinetic energy of 50-gram mass at 10 centimeters, when the angular velocity is 5 radians per second, is that times your 5 radians per second squared. And when you get done multiplying that out, that's 25 radians squared per second squared, and times 5 10,000ths, okay, which gives you 125 10,000ths of a kilogram meter squared per second squared. And that's 0.00625 joules. Now, obviously, I calculated this, and I got 0.0125, because that's like 125 10,000 to be a 125 here. And I had to think about that for a minute, look back here, and say, no, that calculation's correct. This has to come out the same. Well, I'd left off the 1/2 in the kinetic energy, 1/2 I omega squared. So don't do like I do, do like I say. Okay, anyhow, the calculation now reconciles. Now, this agrees with this, so the kinetic energy of the two 50-gram masses would be double this or double this, and it would give you the 0.0125 joules, just as before. Now, the calculation of the moment of inertia here, we could calculate it as 100 grams at 10 centimeters. And we get 100 grams times 10 centimeters squared is 10,000 gram centimeters squared, which would be double the 5,000 gram centimeters squared we had here. And of course, that could be expressed in kilogram meters squared. Okay, so it would be 0.001 kilogram meters squared. And we could multiply that by the square of the velocity and get our 0.125 joules. Now, using the same thing, and this time actually calculating our moment of inertia for 50 grams at 9 centimeters and for 50 grams at 11 centimeters, we get what? 50 grams times the square of 9 centimeters plus 50 grams times the square of 11 centimeters. So we just add the two moments of inertia to get the total moment of inertia. And the first moment of inertia, if you figure it out, is 4,050 grams centimeters squared. The second one is 6,050 grams centimeters squared. They add up to 10,100 grams centimeters squared. Note that that's 1% greater than that. It's 100 out of 10,000 greater than that. 1 part in 100, it turns out, 1% greater, which is consistent with what you get if you use this to calculate the moment of inertia for the system with the 9 centimeter and 11 centimeter positions. And if you do that, you should get the same thing that you get here, at least if you do the calculation completely right, just in case I didn't. And that calculation is 1/2 times the moment of inertia, which I've converted to kilogram meter squared, 0.00101 kilogram meter squared, multiplied by the square of your 5 radians per second. And I claim, actually I don't claim, I assert that if I did all my calculations correctly before, that this should come out the same as this, and that you should double check me on that.